This is our introduction to Chapter 7, which discusses atomic structure, primarily in the electron configuration, and trends on the periodic table. How do we get different colored fireworks? Why do we see different light? Why do burning different chemicals cause different colored flames? Heating up different elements gives us different colors. And then if you put that light through a prism, you get very specific colors of light coming out the other side. Not a rainbow of light, but very distinct lines. This was a question that scientists were trying to understand the answer to as they developed their model of what makes up an atom. So the first thing we need to do is discuss electromagnetic radiation. This is a broad category of different types of energy. The light that we can see, visible light, is a very small portion of this spectrum. It's a way that energy travels through space, and we think about it primarily in terms of waves. And waves have these three characteristics in common, regardless of what kind of waves they are. There's the wavelength, the frequency, and the speed of the wave. Now, the wavelength, as the name implies, is the length of the wave. It's the distance between the top of one wave and the top of the next, or the bottom of one wave and the bottom of the next. The distance between equivalent points on a continuous wave. It's represented by this symbol in equation, so you'll see that for wavelength. The frequency is the number of waves in 1 second that pass through a given point in space. So how often does the wave go by? And then the speed, obviously, is how fast the wave is moving. And in the case of light, and actually in the case of all electromagnetic radiation, whether it's microwaves, radio waves, gamma rays, X-rays, or visible light, they all travel at the same speed. 2.9979 times 10 to the 8th, which you will usually see rounded to 3.00 times 10 to the 8th meters per second. So that's the speed of the wave, represented by c, if we're talking about any kind of electromagnetic radiation. So the fact that the speed of light is constant means that the speed equals the wavelength times the frequency, which means that the wavelength and the frequency are inversely proportional. If one goes up, the other must go down, and vice versa. So here's just a graphical representation of the relationship between wavelength and frequency. So on the top, we have this long wave, or longer wave. The distance between these two peaks up here, or you could say these two troughs, is longer than this distance and longer than this distance. They're about half, cut in half each time. So in 1 second, since they're all moving at the same speed, the longer wavelength has a lower frequency because fewer waves can go through the same point. So longer wavelength means lower frequency, shorter wavelength means higher frequency down here, and then obviously in the middle. So the two things are inversely related, and since they're always equal to c, and c is a constant, that means that if we know the wavelength, we can calculate the frequency. If we know the frequency, we can calculate the wavelength. Here's a representation of the wavelength and the frequency related to, the wavelength related to different types of electromagnetic radiation. So you can see that the shortest wavelength, which would mean the highest frequency, is gamma rays. The longest wavelengths are over here in the radio range, and then in between we have microwaves, infrared, ultraviolet, and this spectrum here, which is the light that we can see. All the colors range between approximately 400 nanometers and 700 nanometers. So that's the wavelengths of the light that we can see. And we could calculate the frequency of those as well. What you're going to see is that the shorter the wavelength, which means higher frequency, means greater energy. Okay, so ultraviolet light is more energetic than infrared light, which has a longer wavelength, which is why ultraviolet is more dangerous in terms of exposure than infrared. So this concept that we're working our way up to of quantum theory has to do with the idea, and this was a revolutionary idea at the time, that energy comes and goes, absorbed and released, in packets called quanta. So for any given substance, any given atom, there's a certain minimum discrete amount of energy that it can gain or lose at any given time. Now you can gain whole number multiples, so you can gain lots of quanta or give off lots of quanta, but any amount of energy that you absorb or release is going to be some multiple of that number, that quanta, or quantum is the singular. And so all this gets to the fact that in addition to wave properties, energy also has properties that can only be explained by thinking of it as particles, which is kind of weird. Usually things are one or the other, waves or particles, but energy and light seem to act sometimes like both. So we can calculate the energy of a photon. A photon is a particle of light by taking this number, Planck's constant, and we multiply it by the frequency. Okay, so again, you can see the higher the frequency, the higher the energy, since the other part of the equation is a constant. Or if you have the wavelength, remember that if the speed of light equals the wavelength times the frequency, then the speed of light divided by the wavelength equals the frequency. So if you have the wavelength, you can substitute the speed of light divided by the wavelength and multiply that by Planck's constant. And that would also give you the energy of the photon. So Einstein figured out, or proposed, that energy has mass. That's where the famous equation comes from. Right? Energy equals mass times the speed of light squared. So we get this idea that light is made of particles and made of waves. When you shine light from the sun, or any sort of white light, through a prism, right, you get a rainbow of colors, the full spectrum that we saw a couple of slides ago of all colors of visible light, continuous. However, when you heat up an element like hydrogen, you get lines of color, okay, very specific lines at very specific frequencies. No, black's not a color, but you get the idea. So every element has this unique spectrum of lines that are given off when you heat it up. Not a continuous spectrum, but just very specific lines. That's called an atomic emission spectrum, or in the case of hydrogen, hydrogen's emission spectrum. And the idea that comes from this, so trying to explain why you only get certain colors from certain elements and connect that somehow to the structure of the atom. The idea is that only certain energy, only certain quanta can be absorbed or released depending on the movement of the electron. And this leads us to the idea of atomic orbitals proposed by Bohr. Okay, so Bohr's model, which is probably the model that most people would be familiar with from, say, middle school science class, has a nucleus in the center and circular electron orbits in rings around the nucleus. And those rings are very specific to each element. So every element has a unique arrangement of rings around the nucleus. The distance between them, and therefore the energy it takes to get from one to the other, is unique to each element. This was Bohr's explanation for why different elements give off different colors, because the distance between the orbits, and therefore the energy it takes to go from one to the other, is unique. So it gives off this effective barcode as electrons move up and down between the orbits. So electrons start off in the ground state. Ground state means that all the electrons are in the lowest possible level. Each level has a quantum number, a principal quantum number, starting with 1, then 2, 3, 4, 5, 6, 7, which is essentially equivalent to the floors in the building. So the electrons start off as close to level 1 as they can be. In the case of hydrogen, it's on level 1 because there's only one electron. Then when they absorb energy, they have the ability to jump from the first level to a higher level. That's called the excited state, okay, because the electrons are at some level higher than their normal state. They take the energy, they jump to the excited state, but then they want to return to the ground state. And in order to do that, they have to give the energy back, because energy cannot be created or destroyed. So they take the energy, they jump up to a higher level, and then when they give it back in the form of light. And because the distances and the energies are unique to each element, the kind of light, the wavelengths of light given off by each element are unique. That's Bohr's model, Bohr's explanation of why things happen this way. So here, just as a sort of graphical representation, we have the energy levels of the hydrogen atom, and we see that as electrons move from level 5 to level 2, they give off blue light here. If they move from 4 to 2, they give off green light, and 3 to 2, they give off red light. And since these are the only levels, and the level 1 down here we're not working with right now, but since these are the only levels and the distance between them are specific, we only get these very specific colors out of a heated hydrogen atom. And if it was a different atom, we would get different colors because the distances between those orbits would be different. So here's just another way of looking at it. Okay, we get the electrons that have jumped up to these higher orbitals, and then when they move back down, they give the energy back in different wavelengths of light, and that's where we get that atomic spectrum for hydrogen. Now, if we want to calculate exactly how much energy we get from a particular jump, a particular transition, we use what's called the Rydberg equation, which is here. So the change in energy from one level to the next is defined by multiplying this constant, the unit here is joules, times 1 over the square of the final energy level minus 1 over the square of the initial energy level. So the energy level, so those are those principal quantum numbers, 1, 2, 3, 4, 5, okay, has to do with how far away the electron is from the nucleus. So the higher the number, the farther away it is. The greater the distance between those numbers, the farther the electron has traveled. And then we multiply that by this constant, and that gives us the energy that's transitioning between those two levels. And we could then turn around and use that energy to calculate the wavelength and the frequency of that light that's given off. And we could tell you what color it would be. And this model worked. Okay? It explained why we get different colors. It was a very unusual way to think about things at the time, but it was a reasonable explanation for why different elements give off specific colors of light. It explained the movement of electrons, how they absorb and release energy, and every experiment that they did on this fit the model. The problem is that it doesn't work as well when you talk about something other than hydrogen, first of all, because hydrogen only has one electron, so it's very simple to model that. Once you have more than one electron, it gets much more complicated. The other problem is that it didn't explain the chemical properties of any of these elements. It didn't explain why some elements are more reactive than others or why they combine in certain ratios. So it was a good explanation of the phenomena at the time, and it gives us the concept of energy levels, transitioning electrons, and the basis of quantum theory. But there's more to it than that, which is what we're going to get to next time, because we need to take into consideration not just how many electrons there are and how many orbits there are, but where the electrons are arranged around the nucleus, and that's what we're going to talk about next time.